So, MYP Physics, we're reaching the end of our electricity unit where we're going to put our knowledge of Coulomb's law, the forces between electrical charges, and electrical potential energy to work. And what I mean by that is we're going to actually try to build proper devices and circuits that convert electrical potential energy into various forms of energy that we use, such as light and heat and mechanical energy in the house. Okay, but in order to get that, we first need to understand what electrical circuits are. Okay, so an electrical circuit is a pathway that we create that allows electrons to flow from high electrical potential energy to low electrical potential energy. Okay, and where we get that stored electrical potential energy is in a battery. Remember in the last video and last weeks of classes, we talked about how ferries inside of the battery store charge on one side, so positive charge on one side and negative charge on the other. Well, it's not ferries, it's a chemical reaction that does that. So these batteries store electrical potential, okay, or electrical potential energy. And when you connect one side of the battery to the other side of the battery, now that there's a driving force to move charge from high potential to low potential. Okay, and as long as I connect it with a conductor, okay, the conductor would allow electrons or charge to flow through the conductor to reach the other side so that all that electrical potential energy can balance out. Okay, so the most important part, as I said over here, the most important part of a circuit is the electrical potential energy source, which is your battery. Okay, and then we have the wires. The wires are the conductors. We usually use copper wires for that. And it would be quite a boring circuit if it was just wires connecting the battery. Okay, if you ever done that, if you ever take a battery and connect just a wire from one end to the other end, what you'll notice is that the batteries get very, very hot over very quickly. And it's actually quite dangerous because the batteries can actually explode if you do that. And the reason for that is that all that potential energy from high potential to low potential is going to be converted into heat inside of the battery. Okay, so we don't want to do that. What we want to do is we want that energy to be released elsewhere. So we have other types of electrical components such as light bulbs or resistors that we can then convert that potential energy into something else. And that's the point of today's lesson. So to look at this circuit, okay, we got batteries, we got a resistor, you got a light bulb, you got a switch, okay, and they are all in a circuit. Okay, a circuit is a complete loop, and these are all placed inside of that loop. Okay, and if I want to look at what an actual circuit looks like on paper, not drawings, but we have symbols for things. These are the symbols for batteries. Okay, this is a symbol for a resistor. This is the symbol for a light bulb. That's a symbol for a switch. So if you search online or in physics classroom, you'll see a bunch of interesting symbols for electrical components, and you'll notice that they're all put into a loop. That's called a circuit. Okay, so as I said, electrical circuit must have a voltage source. That's the most important thing, a battery, okay? And as I showed you before in this diagram, okay, graphite in a pencil is actually conductive. So I can draw a circuit on paper, and as long as I placed a battery cleverly into that circuit, I can actually make a circuit on paper, as you see over here. It's a pretty fun activity. Okay, so there's the battery. It's a flat battery. You have these in your remote controls. Okay, one side is positive, the other side is negative. And when you connect the sides together, okay, with the graphite, and you put an electrical device such as a light bulb, okay, all this is just wiring, we can turn on the light bulb, okay? So that battery is providing electrical potential energy that is being converted into light energy. So all electrical devices, a light bulb, heater, toaster, radio, TV, alarm, they're placed into the circuit so that each device can convert the electrical potential energy into other useful forms of energy, such as heat, light, or mechanical energy. Okay, and the simplest electrical devices that we're going to talk about this week are just devices that convert electrical potential energy into heat. Nothing else, okay? And so how do we do that? How do we do that? So let's first draw out what a circuit looks like. Okay, so that's my battery. Okay, and the long line is a positive side of the battery, and the short line is the negative side of the battery. We call the positive side high potential. Okay, and we call the negative side low potential. Okay, so what does that mean? That means, if you remember in a previous video, if I had a positive charge and I placed a small positive test charge close by, we would say that's high potential energy. Okay, so that little test charge has high potential energy. And when we connect it so that it can see a lower potential, we'd have to connect it with some type of wave of that charge being able to release that energy and go to a lower potential energy. Then all that energy can be released into a circuit. Okay, so how does heat form in a circuit? Well, heat is going to be formed when that charge is doing work as it's moving. Okay, so if I draw a proper circuit with a wire, okay, and we're going to review just a couple concepts that we've already seen before. Okay, so if I have my battery, and let's just say that this is a wire that has resistance. Okay, remember that little simulation I showed before. Okay, now in physics, even though we know it's not true, physics likes to assume that the positive charge is the one that's doing the moving, but it's not. Okay, but we learned a lot about electricity before we even discovered that electrons existed. So whenever you see current flowing and current is the positive charge, that's just a historical idea that positive charge is flowing and it's the high potential source. But in reality, it's the electrons that are moving in the opposite direction. Okay, I just want to make that clear. Okay, so what we discovered last week is that when electrons move through a conductor, they experience something called resistance. Okay, because they bump into atoms, you have to do work to separate electrons from atoms. Okay, and all that work that you're doing to move electrons through a conductor is going to be converted into heat energy. So every time electrons bump into atoms, they make the atoms vibrate, they raise the kinetic energy of the atoms, and we produce heat energy. That's as simple as that. So anytime electricity flows through a conductor that has resistance, the more resistance, the more heat energy is going to be produced. That's one way of looking at it. Or the more electrons flying through a conductor per second, the more collisions you're going to have, the faster the heat energy is going to be produced. And we're going to be exploring that in the next part of this video. Okay, so simplest devices really are just special types of wire that we put into a circuit that allow electrons to bump into atoms inside of that wire and create heat energy. Okay, so those special types of circuits have something called a resistor. Okay, a resistor is any type of device that provides resistance to the flow of electrons in a circuit. Okay, so the most simplest device would have a battery. So here's my battery, here's my wire, and then here is a resistor in the circuit. Okay, and once I have a resistor in the circuit, that resistor is going to create heat energy. Okay, that's the big idea here. So the simplest electrical devices convert the electrical potential energy of the battery into heat energy through the resistor. Okay, and one way you would see that in a diagram, a resistor in some diagrams look like that, and then if you're in an American textbook, the resistor looks like a squiggly line like that. Okay, and we learned that to create a resistor, you just have to have a long length of wire that's very thin, and you're going to create a resistor that is going to create heat. Okay, so I've just introduced to you the idea about a battery, conducting wire, and a resistor. Okay, so the big idea for this lesson is how does voltage, current, and resistance relate to heat produced by a circuit? So if I create that circuit again, and let's say this is a 9-volt battery, and then I put my resistor in here, okay? Okay, another way of drawing that, like I said before, is a box instead of that squiggly line. So if I put my resistor in there, and this is a 9-volt battery, how does voltage, current, and resistance relate to heat? Okay, so first of all, let's remind ourselves what voltage is. Voltage is equal to joules per coulomb. Okay, and current flowing through that circuit is equal to coulombs per second. Okay, so if I have a lot of charge flowing through per second, okay, that charge flowing through is carrying energy. It's carrying joules with it. Okay, for example, the charge that's going to be flowing through this circuit is going to be carrying 9 joules per coulomb of charge. Okay, so if I had 1 coulomb, if I had 1 coulomb of charge flow through this entire circuit, okay, it would release 9 joules of energy. For every coulomb of charge that flows through that circuit, I release 9 joules of energy, okay? So you can imagine, for every coulomb of charge that flies past this resistor, 9 joules of energy is going to be released by that resistor, okay? So that explains it. So as a coulomb of charge flows through the circuit, 9 joules of energy is released by the resistor, and that energy is going to be converted into heat energy, okay? So if I have a very fast current, okay, every second, a lot of coulombs are going to be flying. It's going to be releasing energy, okay? So let's just imagine that I have a current of 10 amperes. So if my current is equal to 10 amperes, that means I have 10 coulombs per second flying through that circuit, okay? And if I had a voltage, if my voltage is 9 volts, okay, how many joules of energy are flying per second, okay? So how many joules of energy is released per second? In that circuit. So here's a circuit that I have 9 volts of energy and 10 coulombs per second. All right, I want to figure out how many joules of energy is released in that resistor per second. Okay, well, 9 volts is equal to 9 joules per coulomb, right? So if I take 9 joules per coulomb and I multiply it by 10 coulombs per second, I can see that my coulombs are going to cancel out. And I'll be left with 90 joules of heat energy is going to be released per second. Okay, do you guys remember what joules per second means? That's the rate of energy. That's power, okay? So in that circuit, I have created a 90 watt circuit. Okay, that should remind you of things when you look at electricity, we think about how many watts something has. Okay, so we just discovered a new formula, okay? So power is equal to the current in a circuit times the voltage in a circuit. Okay, this is current, and this is voltage. Okay, so if I had 10 amperes times 9 volts, that is going to give me 90 joules of heat energy released per second. Okay, so inside that circuit, I'm going to have 90 joules of heat energy released per second. Okay, so if I draw that out again, let's imagine this is my resistor with that squiggly line. All right, in this circuit where I would have 9 volts and 10 coulombs per second of current, okay, or 10 amperes, I would be releasing 90 joules of heat energy per second by that resistor. Okay, so and if I put that resistor into a cup of water, so here's my cup of water, and I have that resistor inside that cup of water, okay, and that's my battery, okay, it would be releasing 90 joules of heat energy per second into the water, which I could measure by measuring the temperature change of the water. Okay, so we're going to be doing a few more videos about this, but just to give us a little bit of a lowdown, what we covered today, right, in this little video, is understanding what does an electrical circuit look like. Okay, it has a battery, it has wires, it has electrical components in it that convert electrical potential energy into other things such as heat and light. Okay, we talked about the simplest device that has just resistance in it, nothing else. So if I have a battery and wires and I connect it to a material that has resistance, that material allows the electrical potential energy to be converted into work. Okay, and that work is going to be converted into the kinetic energy, those particles inside of that wire, which is going to be heat. Okay, so one thing I think about is resistance. A resistor creates heat energy or transforms heat energy from electrical potential energy. And the resistor looks like a box or a squiggly line, depending on what textbook you're looking at. And the biggest idea of this lesson is, how does voltage, current, and resistance relate to heat produced by a circuit? Well, I talked about voltage and current. If I multiply the voltage in a circuit by the current in a circuit, I'm going to get the power. Okay, I get the power of heat produced. Okay, so power is equal to current times voltage. That's what we talked about. All right, but we didn't really talk about resistance, but you can understand that if I put resistance into the circuit, it's going to change the amount of current that's going through the circuit. It's going to slow it down. Okay, so the more resistance I have, I slow down the current. I might affect the amount of heat that is going to be created in that circuit. Okay, so we're going to do a little bit more practice with this relationship in the next video.